Now what we're going to do is continue on to 11.2, talking about our constructions with counting objects, counting events, where in particular we're going to look at a special case that occurs when we want to count things where we don't get repetitions and order matters. So to understand what we're looking at here, let's start with an example where, say, you go to a race and there are 8 runners in the race and you want to pick the winner for no particular reason because gambling is still illegal in Florida. But let's say you want to pick that winner in the race. So it stands to reason that you will have 8 options for first place. Now, from there, you can think about what might happen to the next one. So if you want to get the person in second, well, can't get someone to finish both first and second at the same time. So whoever came in first can't also come in second, means you've got 7 of them left over. And then if you want to think about third, you would get, can't be second, third, can't be first and third, or second and third. So both of these two are taken. You get 6. And you could keep on going down the line. You would get that for fourth, there'd be 5. Fifth, there'd be 4, 3, 2, and 1, all the way down, because someone does have to finish in last place and they can't get any other position. The idea here is if you take all of those options and you add them up, in this case multiply them out, by the fundamental counting principle, which I'm going to abbreviate FCT, we have 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 options in total. Because we've got 8 ways to get the first, 7 for the second, 6 for the fifth, 6 for the third, and so on down the line, where we multiply our number of options in each case out. And that's how we get our total number of options. And then if we want to think about something more specific, like let's say, in particular, we only want the top 3, because sometimes for those of you who are in states where gambling is legal, you might talk about placing. That's usually what they mean for the top 3. We would have 8 options for first, 7 for second, and 6 for third, where if we multiply these terms out, you want to get it actually in terms of a number, we have 40,320 ways that we can get any of them, that we can get all possible arrangements for all 8 racers, whereas we would only have 336 ways to get top 3. That's nice. It's not too hard for 8, but even there, you saw that, like, if I'm going to go through every single case, it takes a little while, and if I had more than 8, it'd be really clunky to write that out, and it'd be even clunkier to multiply it. So, in order to make our life a little bit easier, we actually have a nice notation for talking about things like this, for talking about what are called descending products, where we multiply each of these terms down the line, where what we can do is when we talk about that value 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, we can condense that whole thing down to 8 factorial. So that's how this is read, as 8 factorial. It doesn't mean that the number 8 is very excited. It means that we take 8, multiply it by every single one of these natural numbers smaller than 8. And then we do all that, get a number of that form, where, in general, we have a construction n factorial, such that n factorial is equal to n times n minus 1 times n minus 2 times n minus 3 times n minus 4, all the way down until you get to the very end, 2, and then finally you multiply it by 1. Technically speaking, you don't have to write out that you multiply it by 1, but you still do. And specifically, we have one case in particular where we say that 0 factorial is specifically equal to 1. And there's kind of a cheap reason for why this happens, and it's because there's some constructions we'll talk about later where if we made 0 factorial anything other than 1, it would cause a lot of problems. But the other way we can think about this is in terms of what we're representing with this factorial up here, with that value 8 factorial. Because when we discuss factorials, what we're trying to do is find the total number of arrangements where we specifically care about order, and we're taking every single one of them, so each time you take one, you have less options for the next case. So we're talking about arrangements of some number n things in order. Well, technically speaking, the only way you can arrange 0 things in order is just by having the 0 things. So we trivially say that 0 factorial is equal to 1.